Last time, we managed to get a single cube spinning on our screen. It's awesome, but let's be honest, staring at one floating box, we can do better. What if we want the whole world? Floor, some buildings, and most importantly, what if we want to actually fly inside it? Well, today we are taking off the training wheels. We are turning our single cube viewer into a free-fly 3D scene covering multiple objects at once. To do this, we need to completely rethink how we store data. In our new code, you'll see three brand new structures. First, a vec3d to neatly hold our x, y, z and w coordinate for future-proofing. Second, a triangle structure that groups three of these vectors and attaches a color to the face. And finally, the most important one, the block structure. Why do we need a block? Well, a single cube is made of 12 triangles. If we want to build a city, we are going to be dealing with plenty of triangles. Managing them loosely is a nightmare. By grouping 12 faces and the central coordinate into a single block, we can treat a building as a solid single entity. To hold our city, we drop these blocks into a dynamic list, std vector, called world blocks. Down in our onUserCreate function, I've set up a double for loop to generate a procedural grid. It iterates x from -3 to 3 and z from 8 to 15. Notice the starting z value. We deliberately spawn the world far in front of the camera so we don't start inside the wall. It lays down floor blocks and then, using a bit of randomness, stacks a few blocks vertically along the negative y-axis. Because remember, y goes down in screen space, so negative y goes up into the sky. We use a rand here because we don't care about precision or true randomness, really. But remember, you should always prefer the random library in most cases. We now have a procedurally generated world. To explore it, we need a camera. In real life, if you want to look at a house from a different angle, you walk around it. But in computer graphics math, a camera doesn't actually exist. The screen is a fixed window. So how do we create the illusion of movement? Well, it's simple. If I want to take one step forward, I just grab the entire universe and put it one step backward. If I want to look to the left, I rotate the entire world to the right. To make this happen, I've introduced a few camera variables. Camera pose for where we are standing, yaw for looking left and right, and pitch for looking up and down. We hook this up to the mouse inside onUserUpdate. By calculating the difference between the current and the last mouse positions, we change our yaw and pitch. Notice that I'm clamping the pitch between -0.5 and 0.5 radians. This is crucial. Without this, you could snap your neck, flip the camera completely upside down, and your controls would instantly invert. This phenomenon is related to gimbal lock, and clamping keep our math sane. Now, how do we physically walk through this space? You might think, oh, pressing W just increases the camera's Z coordinate. No, that only works if you are staring perfectly straight down the Z axis. If I turn 45 degrees to the right and press W, I need to move diagonally through the world. Look at the code where we calculate it forward. We are doing some serious spherical trigonometry here. To find the exact 3D coordinate our crosshair is pointing, we have to combine our angles. Our x movement is sine yaw times cosine pitch. Our y is minus sine pitch, and our z is cosine yaw, cosine pitch. It looks intense, but it just creates an invisible mathematical arrow of length 1, pointing exactly where we are looking. Pressing W takes that arrow, multiplies by our speed, and adds it to our camera position. Pressing S, subtract it. For strafing left and right with A and D, we'll calculate a right vector. But notice I completely ignored the pitch here. By setting the right vector to just cosine yaw and sine yaw, we keep it strictly horizontal. This ensures that when you strafe, you slide nicely across the floor instead of accidentally flying up into the sky or burrowing into the dirt, based on where you are looking. I also added R and F for dedicated vertical flight. Alright, so the world generates and the inputs are mapped. We boot it up and Yeah, it looks like MC Escher painting. Triangles from a building in the background are rendering over the buildings right in front of my face. It is a complete visual mess. Because we are storing blocks in an array, the computer just loops through and draws them in the exact order they were generated. It has no idea what the depth is. If we draw a distant cube last, it overrides the pixels of the close cube. To fix this, we channel our inner Bob process. We are going to implement a hierarchical painter's algorithm. Think about how you paint a landscape. You paint the distant sky first, then the mountains, then the trees, and finally the happy little bushes right in the foreground. We need to do exactly that. Before we draw a single pixel, we look at every block in world blocks. I wrote a tiny lambda function called getDistanceSquare that calculates the squared distance from the camera to the center of each block. Why squared? Well, because calculating through distance requires a square root, and square roots are really expensive. For sorting, we don't need the exact distance in meters. We just need to know who is bigger. We use stdsort to reorder our blocks from furthest to the closest. Just a little side note. In GPU programming, the sorting is usually reversed. You want to draw the closest object first and keep the rest on your graphics card. By doing that, we are preventing, or at least minimizing, what is known as overdraw. In that settings, we prefer to draw every pixel once, but here in our case, we keep things simple from an implementation perspective for now. So as we loop through these sorted blocks to draw them, we apply our view transform. Order matters here. First, we translate. We subtract the camera's position from every vertex. This physically drags the entire world, so the camera is mathematically sitting perfectly at 0, 0, 0. Then we rotate the vertices by negative 0 and pitch to spin the world around our eyes. We talk about all of it in the previous videos, if you want to check it out. Because we move the camera to 0, 0, 0, our backface cutting gets a neat upgrade. The line of sight ray from the camera to the triangle is literally just the coordinate of the triangle's first point. We take the dot product of the face's normal vector and that point. If the result is greater than 0, the face is looking at us, and we proceed. The city is sorted and the movement feels smooth. Let's walk right up to one of these buildings and pikes, giant flashing polygons tearing reality apart, stretching to infinity. If you ever try to program a 3D engine from scratch, you know exactly what this is. This is the rite of passage, the dreaded projection explosion. What caused it? Well, when we project 3D to 2D, we divide the x and y coordinates by z to simulate perspective. But what happens if we walk past the vertex? Yeah, its z coordinate becomes negative. If you divide x and y by a negative number, the point aggressively flips to the complete opposite side of the screen. Even worse, if z hits exactly 0, dividing by 0 causes a total math meltdown. We cannot let vertices get behind our eyes. We need a shield. We need a near plane z clipping. Imagine an invisible pane of glass sitting exactly 2 units in front of your camera. This is the near plane. If a triangle tries to pass through this glass, we take a pair of geometric scissors and cut it. This is exactly what the massive clip against z-plane function does. We check all 3 points of a triangle. If they are all behind the glass, we throw the triangle away. If they are all in front, we keep it. But there are 2 tricky scenarios where the triangle physically intersects the glass. Let's look at the helper lambda inside the function intersectZ. It asks a simple question. What percentage of the line lies in front of the glass? It calculates a ratio t by looking at the depth z and then uses that percentage to interpolate the x and y coordinates. Pure linear interpolation to find the exact molecular point where the line touches the glass. Scenario 1. One point crosses behind the glass, but the other 2 are safe. We chop off the point that's behind the camera. But wait, a triangle minus a tip is trapezoid. Our graphics engine only knows how to draw triangles. So we use our intersect Z map to find where the 2 lines hit the glass, and we construct 2 brand new smaller triangles to fill that trapezoid shape. Scenario 2. 2 points fall behind the camera, leaving only 1 point visible. We chop off the bottom and we are left with a smaller triangle. That's easier. We find the two intersection points on the glass and output one new, perfectly clipped triangle. We run through this clipping math right after the view transform, but before perspective divide. By doing this, we absolutely guarantee that no vertex with a z value less than our near plane will ever make it to the division step. And finally, just to be absolutely bulletproof, right before we call fill triangle, I added a quick safety check called is dangerous. Even when clipping, extreme edge cases can occasionally throw a 2D screen coordinate out to negative 10,000 pixels. This little boundary check just ensures we don't accidentally ask to draw a triangle the size of a continent, which would lock up the program. I'll plug all of this into our pipeline, and now let's walk. The wall glides right past the edge of the screen, perfectly clipped. No explosions, no spikes, just pure 3D immersion. As you can see, performance is not good. Let's leave it like that for now and optimize in a future video. And there you have it. We've evolved from a simple spinning shape into a full navigatable 3D environment. We tackled camera view matrices, spherical vector math, hierarchical depth sorting, and the legendary first-term clipping algorithm. Play around with this code, build bigger cities, and tweak the movement. There is a link for a playlist with more information about 3D graphics programming, but if you want to remind yourself of the basics about rendering the one pure rotating cube, click here. That will be all for today. Thanks for watching. If you want to see more in the future, just hit the subscribe button and ciao!